Welcome back to Arts Learn. In this video, we'll be going over ideal and actual mechanical advantage, as well as what they mean, so we can explore how it ties into pulleys later on, okay? First, before that, let's understand what mechanical advantage is. MA. This is the advantage produced by a machine, okay? So basically, what this means here is if, for example, I had a fulcrum here, right, and a seesaw. If I had a very heavy weight here, but over here it's pretty short arm, right? But over here, I had a very long arm and I still pulled down. It would feel easy to get this block upward. Why is that? That's because I traded force for distance. Okay? So if you ever see a car mechanic, he puts up something under the car, right? And then he presses something to move it up. He doesn't move it up himself. He keeps pressing it repeatedly, which moves it up himself. What he does is he trades force for distance. Okay? So the energy has to be equal in both scenarios, okay? How much energy you exert and how much energy the load exerts are both equal here, because energy can be created or destroyed. F effort times D effort is equal to F load times D load. Okay? So then, energy initial is equal to energy final. But the thing is, you can change up these values, right? You can move F load and D load downward or upward, but you can still keep the same energy. That's what machines do, okay? You have to exert them over a longer distance. So that's why for a car jack, right? For a car jack, you have to push the car up multiple times. I mean, you have to push the jack down multiple times. But guess what? It pulls the car up, right? It pushes the car up. You can't imagine doing that with your own force. So what happens is, the force here is traded for distance. You use a larger distance, so D effort is larger, okay? But F effort is lower. You don't have much force, right? You just keep using more and more distance. And then you don't need to exert that force. The machine exerts that force for you. That's why even if you're not strong enough to lift a car, which nobody is, right? You can repeatedly use distance to leverage and gain force, okay? You don't exert that force, the machine does. You can trade force for distance. That's the thing with pulleys, okay? If you have multiple pulleys, right, attached to a weight, which we'll go over soon, if you pull this string here, if you pull it to the right, then it goes down, right? And it should feel easy. It's going to feel easy, but you need to pull it to a long distance to get these weights to go all the way up. Okay? Because why? The pulleys are exerting the force for you. You're trading that force for distance. So you're not putting it so much effort as in force, but you're putting it more as in distance. Okay? So that's what machines do. An ideal mechanical advantage is calculated using D effort over D load. So what that means here is, if I am, same example, right? D effort is the amount of distance I pull the machine, I use on the machine, right? So D effort is going to be a larger value than D load. D load is how much the machine pulls on this. The machine doesn't pull as much distance, right? Because it pulls by force, right? Or the distance of the load. It's not, so the load itself isn't pulled up by the distance, right? It's the machine generates the force to pull it up, because you traded force for distance, you pull it longer, and then it trades distance for force, and it uses that force to pull it up. Okay? So ideal mechanical advantage is D effort over D load. Basically, if you pull this 3 times as large, okay? 3 times as large, 3s, then this, but if you use 3 times lesser force, your mechanical advantage would be 3, okay? So let's go over how that works in problems. If you're given an inclined plane, okay, and IMA, you ask for the IMA, okay, ideal effort, ideal mechanical advantage. Ramp length is 6 meters here, height is 1.5, load is 200 newtons. IMA, ideal mechanical advantage, would be what? It would be D effort, right, which is how much you're pushing it, which is 6 meters here, over ramp height, which is 1.5 meters. Now, why is that? Ramp height is what is over here, right? That's the distance pulling down on you over here. The force times distance. The MGH here. That's what's pulling you down here. You're moving it that high. Instead of just pulling it up 1.5 meters, what are you doing? You're pushing it 6 meters, but with lesser force, right? So it's going to feel easier to push this up a ramp than to lift it up simultaneously to 1.5 meters, which makes sense, right? So how much distance did you push it up the ramp, and how much was the actual weight itself? 1.5. So 6 over 1.5, your mechanical advantage is 4. Okay? Now let's go over how it looks in a lever. You have a load arm, which means a 600 Newton block at 0.3 meters here. And you have an effort arm, which is 1.2 meters. Okay, so how much is your ideal mechanical advantage? 1.2 meters over 0.3 meters, right? Because this is your distance. This is the distance of the block. Or 4. And that's just ratio, so I mean, it doesn't have units. So ideal effort, which we'll go into later, but think of it like this, right? Force effort times distance effort is equal to force load times distance load, right? So IMA is effort arm over load arm. And then if you find the ideal mechanical advantage, you know that, what do you know? Distance effort has to be 4 times as large, which means force effort has to be 4 times lesser than force load, right? Force load is 600 newtons, so divide that by 4 and you get 150 newtons. Okay, so for ideal mechanical advantage, just D effort, which is how much you use, right, over D load, is IMA. And force effort, right, force effort times IMA is equal to force load. Or, I mean, if you want to be more intuitive about it, it's equal to force load over force effort. Okay? But this is very dangerous here, okay? This, I know what my IMA was because I got that from the distance thing. That's why I used it to find this, okay? But this is actually actual mechanical advantage, okay? Your ideal mechanical advantage will always just be your distance. Your ideal mechanical advantage relates to distances. Distance of effort over distance of load. Okay? This is how much force you actually spent, because sometimes that force is altered, right? That's what's your actual mechanical advantage. This is in a perfect dream world, okay, where nothing alters. But we can still use it to find our actual force, okay? So again, you just use the ratio and you need to kind of think through it. Where's it going to go? So let's go over some problems here. A ramp is, let me zoom out. a ramp is 8 meters long. Okay, 8 meters long and 2 meters high. Ideal mechanical advantage is an ideal effort. That's why it was ideal effort, right? That's why I didn't say the actual effort, force of effort. Ideal force of effort. So instead of just lifting the block straight up 2 meters, I'm pushing it 8 meters, right? So I have an advantage there of 8 meters over 2 meters, because I could have just did 2 meters, but I did 8 meters. So my ideal mechanical advantage here is 4. Okay. What is the ideal effort to raise a 300 Newton load? So I know that my distance here, my force in times distance in, is equal to force out times distance out, right? If I know that my distance in over distance out, which is 8 over 4, right? So force in times distance in over distance out is equal to force out, right? Because I can just divide by both on both sides. And I can separate the F in from that. We know this is just, what, 4, right? So force in is my ideal effort. So that's just going to be force out divided by 4. Or 300 newtons divided by 4, which would just give me about, well, let's see here, it should be 728, right? 28, and then what? 75. So 75 newtons of force is my force in. So you need to do, so ideal effort actually, because this is using ideal effort, right? Ideal mechanical advantage, not actual. So here, that's fine, okay? Because they said ideal effort. And you didn't need to do all this math here. You could have just said, you know, force out over force in should be your ideal mechanical advantage. Or you could have just reasoned through it, right? If my ideal mechanical advantage is 4, what does that mean? I exert 4 times lesser force than this, right? So this is going to be 300 newtons over 4. Okay. Now let's go to number 2. Okay, so pulley system has 5 rope segments supporting the load. IMA, then rope pulled to lift a load 3 meters. So 5 rope segments, okay, so 5 ropes here. So I'm just denoting them as pulleys, but they could just be hanging ropes, right? Then over here, some load. Okay. So how much do I have to pull to lift the rope 3 meters? So my ideal mechanical advantage for pulleys is the number of pulleys, right? Because the number of pulleys I have, that much times easier it's going to be lifted. So my ideal mechanical advantage here is going to be 5, because there's 5 rope segments. And if you didn't understand that, that's fine, okay? I'll go over it more in my pulleys video when I cover that. So that's all good. Then what's the rope pulled to lift the load 3 meters? So how much rope did I pull to lift it 3 meters? Ideal mechanical advantage is distance in over distance out, right? If the load is lifted 3 meters, that's distance out. So 3 times 5 is my distance in, which is 15 meters. Okay, because this unit here for 5 times 3 meters is meters, right? Okay. A lever has a 90 centimeter effort arm, so 0.9 meters, and a 15 centimeter load arm, or 0.15 meters. What's my ideal mechanical advantage? That's my effort arm over my load arm, right? 0.9 divided by 0.15, which is about 6, because that's distance in over distance out again, right? This is my distance in, this is my distance out. Okay, a single movable pulley supports a load. So it looks like more like an Atwood machine here, right? What is your ideal mechanical advantage? Well, how many pulleys do you have? One, right? Your ideal mechanical advantage here is just one, which means distance in over distance out is 1. And you can understand that distance in is equal to distance out. So you basically have just one or no mechanical advantage, right? Okay, so now let's go over actual mechanical advantage as well as efficiency. So actual mechanical advantage is the opposite of ideal. Okay? Ideal mechanical advantage was distance in over distance out, because we were trying to see ideally what would be the mechanical advantage given how much distance it traveled, okay? But for actual mechanical advantage, it looks at forces. So force of load over force of effort, or force out over force in, because these are always going to be greater than 0, right? I mean, most of the time, greater than 0, greater than equal to 1. Most of the time, okay? Sometimes there's race scenarios where machines trade force for distance, and they want more force instead of more distance. But we won't get into that right now. So force out here, or force in. Force out is going to be the greater force, right? Because the machine is exerting a greater force. It's going to be greater than force in, which means this ratio here is also results in a similar answer to this, right? Same greater answer here. It's going to be a valid large answer. So that's what this does here, okay? Now what? Now you have to understand that actual mechanical advantage is always lesser than ideal mechanical advantage, because actual mechanical advantage deals with a lot of friction, right? So you might imagine in a perfect world that with a pulley, right, you can pull it up. So if it's 2 pulleys, you can pull it up with the ideal mechanical advantage of 2, which would be right? But this is ideal. Your actual mechanical advantage, which is your force out over your force in, has to compensate for the force of friction between the pulleys. So it's going to be lesser here. The force out isn't going to be as efficient as you think it is, okay? So lesser force out over the same, lesser force in over the same force out. Because the force in is what you're putting in, right? You have to compensate for the friction yourself. So it's always going to be lesser than IMA, because you have to account for real world scenarios where you have to exert more force than ideally necessary, right? Because of lots of things. So then let's look at efficiency. Efficiency is basically just how efficient the machine is. And how do you measure that? You look at how close it actually is, right? So efficient. So even in real world, right? Efficiency is just how productive it is, right? How much is it putting out? How efficient is it? How much are we getting done here, right? How much efficiency, yeah. So AMA over IMA. Or how much is it actually getting done, right? Over how much it's supposed to get done. So if it gets everything done that it's supposed to get done, then the efficiency is 100%, right? If it doesn't, then it starts to subsequently decrease. So that's how this works, okay? Your efficiency is your AMA over your IMA. This times 100% is just to denote that efficiency is measured in percentage, okay? So you're not going to see efficiency just like a ratio, although you might, but mostly you see it in terms of ratios, okay? All right, so now let's move on. Let's look at the actual mechanical advantage as well as the efficiency of a pulley. If you have a load of 500 newtons, okay, and your actual effort, so your actual effort is 150 newtons, so you're pulling in with 150 newtons here. Your ideal mechanical advantage is 4. So your actual mechanical advantage is your force out, because force out has to be greater than force in, right? Over your force in, which in this case would be 500 newtons, right? Over force of in, which is 150 newtons. Newtons cancel out, you're left with about 3.33. Okay? What's your efficiency going to be here? Efficiency is just your actual mechanical advantage, which is 3.33, over your ideal mechanical advantage, which is 4. We're seeing how much it's getting done that it's supposed to get done. Is it doing all of it or not? So here you get 0.8325. You multiply that by 100%, and you get 83.3%. Approximately. Okay, you can say 83.25, but I'm just going to round up here. So yeah, friction could have turned that into heat, right? Because energy always is constant. It didn't just go away. The energy has to be the same. It's just that in this world, friction, sound, all those things take away the energy. So we often don't have exactly how much energy we started with. So now let's look at the actual mechanical advantage of a car jack, okay? So a car jack lifts 4,000 newtons with 200 newtons of effort. So 4,000 newtons here is what? Force out, right? It's how much it's lifting. So it's the force out. How much force the machine exerts. The 200 newtons here is the force in. That's how much you're putting in. So your actual mechanical advantage is going to be your force in. I keep saying it wrong. Force out over force in. Okay, because ideal mechanical advantage has that flipped. Distance in over distance out. And you know that both of these need to be the same, right? Because the ratio here has to be same. But both have to be greater than 1. This is the greater term. This is the lower term. Greater term, lower term. Okay? So 4,000 divided by 200 is equal to 20. And that's going to be what? Our actual mechanical advantage. That's it. Not that hard this time, right? You can't find IMA though, because IMA depends on distance. So we just have to leave it over there. Alright, so let's go through some problems together. A jack lifts 4,000 newtons with 200 newtons. What is the actual mechanical advantage? You know, this formula is again force out over force in, right? Because this should give us a value greater than 1. And the machine is exerting more force. So this is going to be larger than the force we put in. So 4,000 here, newtons, divided by 200 newtons. This is R20. Over here, IMA is 5. Okay? And 250 newtons of effort lifts 1,000 newtons. What is our actual mechanical advantage in our efficiency? 250 newtons here is our effort, right? So that's what? Force in. How much we're putting in. Lifting for 1,000 newtons, that's force out. That's how much the machine is lifting, right? It has to match up to this and then move it upward. So actual mechanical advantage is force out over force in, or 1,000 over 250 because the newtons cancel, right? Or 4. And our efficiency, let me actually box this answer first, is our actual mechanical advantage, how much it can do, versus how much it's supposed to do, right? How much is it doing of what it's supposed to do? Or in this case, 4 divided by 5, which is just 0.8. Then that times 100% should give you about 80%. Okay? Now, a ramp has ideal mechanical advantage of 4. Friction drops actual mechanical advantage to 3. What's our efficiency? Actual mechanical advantage over ideal, which is just about 0.75. But always remember, this should come as a percentage, right? Or, in this case, 75%. Now, a movable pulley has an initial mechanical advantage, ideal. Initial is for kinematics and force, right? Of 2, and you apply 180 newtons to lift 300. This, whatever you apply, is force in. Whatever you lift is force out. Our actual mechanical advantage is force out, 300 newtons, over force in. And in this case, that should be about 1.67. Okay? And then our efficiency here is going to be our actual mechanical advantage, right? So F is equal to actual mechanical advantage over ideal. Or 1.67 divided by 2, which would give us 0.835 times 100%, or 83.5%. There you have it. That's your answers. And next video, we'll be going over pulleys as well as rope counting, okay? So these problems may have seemed a tad bit easy, but now we're going to apply those concepts into pulleys. Some pulleys get a tad bit complicated in terms of like where you have to measure the ropes, which ropes you have to count as mechanical advantage, and a bunch of complicated stuff, okay? So, well, just get ready, right? And make sure you give me a like and subscribe so I can help you out, as well as keep helping others out. Thank you for watching.